Hello everybody, welcome to Discrete Math, an intro to a little scuffed introduction to it. We'll be starting off with propositional logic, and let's get straight into it. I won't be covering too much immediately, and propositional logic will be the first thing that I will cover in its entirety in under an hour. It took an hour to learn this entire thing, but I have to summarize it in less than that, in under 30 minutes, because I know that most people's attention span does not last as long as 1 hour, and well, I'm the one who took the class. You guys aren't here to take a class. You guys are just here to watch an entertaining YouTube video more often than not. So anyways, what is propositional logic? We have propositions. And what are propositions? Well, propositions are basically a statement that's true or false. That is basically what a proposition is. As in, the sky is blue. That statement is true. Currently, because it's the morning, but if it's like the afternoon, sometimes it's a bit red, sometimes it's kind of green, depending on how the light acts during the day. I've seen green skies before, not usually, and also the sky sometimes, often, very dark purple, blue, black when it's nighttime. Oftentimes it goes into like a little red hue and then it goes all the way there, but the sky is blue is true. But of course, we actually have a unique symbol for when it comes to stuff. Let me go ahead and do that real quick. When it comes to logic here, we use 3 lines to indicate equivalencies between truth values and stuff like that. It's the same thing as an equal symbol, which is why I just typed in an equal symbol, but we use this symbol here. And this is basically what proposition is. And say another proposition, I suppose, well, that's basically what propositional statement is. We don't need to cover too many examples. Whatever statement that can be defined as true or false is basically it. And generally there are 2 truth values, true and false. Of course, there's also this in the middle truth value, which is called indeterminate. But thing is that we don't actually care about that. I did not learn about that when I took discrete math, and honestly, that's something that either you're gonna have to learn in your free time or something that you'll probably learn as you go further into deeper math. But for an introduction and for what I've learned in college, we do not care about that. We're going to keep it nice and simple. Now, there are 4 functions that we can apply to propositions, which are the not symbol. I'm actually going to have to draw it because I don't want to look for the ASCII symbols. The or symbol. The and symbol. The implies symbol, or the implies function symbol. Doesn't really matter. They're both, the symbol represents a function anyway. And there's also XOR and NAND, which is basically this. And this is XOR for what it's worth. There's like a unique symbol associated with it, but I couldn't find it before. So, why don't we? I don't actually. Why am I? Okay, let me just real quickly. Yep. So we have not or. Maybe I should use caps lock. There we go. And don't need that. Applies XOR NAND. These are all the functions that basically apply. Now, not has a few different symbols related to it, including just like a bar above something. Oh yeah, propositions are also represented by variables such as P, Q, and R. Probably could have just used the text there, but instead I decided to write it out. P, Q, and R. We don't want to like write the sky is blue and the apples are green, or the water is red and the earth is orange. Like, we don't care about what the general composition of the statement is. We just care about its truth value, and we can just represent the entire statement as is with one of these variables here, a propositional variable, which doesn't, so that way we can simplify it and do fun stuff with it. And of course, we have negation here, we have conjunction with the and, we have disjunction with or, and exclusive disjunction, and well, I think you can fill in the rest with NAND, which we can also go ahead and do a little truth table as to how each of these operators work. So we have P and Q, and we have a few, there's, it doesn't really matter what proposition they're actually saying. They can either have a true, they could both be true if we're trying to have them get interacted with each other, or not. So could be true, it could be false, it could be true, it could be false. A random there are only 4 possible combinations of each two for all possible things. Of course, there is the indeterminate stuff, but we don't care about that yet. We do not care about that yet. So we have not P, which can also just be represented as P bar, or you can also just go ahead and write not P entirely as well. And the only thing that will do is just flip the truth value around. And that's what it does. It's very, very simple. But what about the and symbol? P and Q. We're basically trying to figure out if both of these conditions are true, if both of these propositions are true. And in this case, you see that P and Q are true within this combination, so that's true. But as you can see from the bottom of the list, F here, 2 F's here, none of the below here is basically actually worthwhile. It's basically like, well, actually, I don't even know if this is the correct symbol for XOR, but fuck it, we ball. But because as long as any one of those symbols are effectively false, it's P is true and Q is true, and if not and, like if both of them aren't true, then and doesn't really apply. Apples and bananas. Well, we don't have bananas, so can we really say that apples and bananas is a true thing? But if we had something else, say P or Q, well, as long as, I have apples or bananas, doesn't really matter which one I have, so long as I have one of them, it'll be true. I have both. In this case, I have P and Q, P or Q, but I only have P here. But I did say P or Q. So I do have P, so yeah, I have that. And in this case, I don't have P, but I do have Q or Q. So that's true, but I don't have either in the bottom combination of truth values, so this is false. That's basically what or is. And of course, now we have this funny little implies here. This little fun thing is a bit of a fun experiment for you, because now we're going to get into the concept of vacuous truth. Vacuous truth is effectively what I would like to call a pain in the ass. Now, let's go ahead and make a little thing here. We have P, and we want to have it imply, this is a propositional statement, this is a statement, and it has to imply Q. And what does it mean by imply? Well, it's not the same as cause, but it's similar enough that you can go ahead and think of it, though I really wouldn't recommend conceiving it as such, because you are genuinely going to hate yourself and try and struggle to understand anything. It is if P then Q. It's like a hypothesis. If water falls down, then this bucket of water will fill up. But if the bucket doesn't fill up, then the statement is not true. However, it might be because the bucket doesn't have a hole or something like that. And so that's what basically P implies Q is. If P, then Q. P only if Q. And P is sufficient for Q. That's like the... P is P only if Q. Yeah. That's the natural way to say how to express these types of implied statements. Like what I came up with before. Let's go ahead and write that down, actually. If water falls from this pipe, then it will fill up the bucket on the bottom. And we can go ahead and outline the statements here. This is P. Water falls from this pipe. Then this is Q. P implies Q. And so the thing is that it basically is this happening. If it's true, then it implies true, or rather, it's not, it should imply true, but basically, if water falls from this pipe, let's express in natural language first, to make it more understanding. If water falls from a pipe, this is true. Let's go ahead and actually write this down a little bit. Real quickly, real simply. True, true, false, false. And true, false, true, false. So right now we have this here, where water falls from the pipe and it will fill up the bucket on the bottom. And basically, what this is basically doing is treating this entire statement here, this entire thing here, as one statement, effectively, as best as I can put it anyway. If water falls from this pipe, and it's true, that statement is true, then it will fill up the bucket on the bottom, and it filled up. That's also true. Q is true. The proposition Q is true. Then basically this entire statement here where P implies Q, let's actually go ahead and move that to the truth table up above and also below. Why don't we also just keep it down here anyway, but I'm going to also put this onto this little thing here. We basically know that this entire statement is true because both things were true. If water falls from this pipe and the water filled up on the bottom, then yeah, this entire statement is true. Yeah, because the water, not really because of the water. If the water falls from the pipe, then naturally we would assume that it would imply it is sufficient. It is enough for the bucket on the bottom to be full. So this entire statement can be true. But what if, suppose, that the bucket on the bottom isn't full? The water's still falling, but the bucket isn't full for whatever reason. Well, then this statement is false, then. Because P does not imply Q. So this is entirely false. It doesn't imply that. Just because the water falls from the pipe doesn't mean the bucket's going to be full, because the bucket's not full. Doesn't apply that. It doesn't. It's not sufficient for it. It's not. If water falls from this pipe, it doesn't necessarily mean that then the bucket will be full. Because Q is false. Because the bucket on the bottom is empty, so we don't have to worry about doing all that kind of. We don't have to. This entire statement is basically whatever. It's false, basically. But here's the weird thing here. P is false, and Q is true. Though this also kind of just falls into the same little issue here. Where the water is not falling from the pipe at all, but the bucket on the bottom is full. Well, the thing is that this statement isn't necessarily false, because the thing is that if water doesn't fall from the pipe, then we can't carry on with our statement. Basically, if water doesn't fall from this pipe, whether or not the bucket can be full, the bucket could be full despite water not falling from this pipe. In the same vein, even if water doesn't fall from this pipe and the bucket is empty, it doesn't necessarily mean that this entire statement is false. It's only applicable if water falls from your water collecting drain. It only applies for that case. So basically, we have this thing called vacuous truth. Vacuous truth is effectively when P implies Q is true when P itself here. The implying proposition is true. Or not true, false. Vacuous truth is effectively, in Boolean, the same thing as truth, but we need to watch out for this because it's not actually true. It's vacuously true. It's just, technically it's correct because there's no way to actually prove it false, basically. Because whether or not the bucket on the bottom is full or not, if water does not fall from this pipe, then there's nothing to prove, because the statement is if water falls from this pipe, then it will fill up the bucket on the bottom. But if water does not fall, then this statement doesn't say anything about water not falling from this pipe. It says only when water falls from the pipe. It's not about whether or not the water falls or not. It doesn't really matter if it does. It's when the water falls from this pipe, then we can continue on with our implied statement. And so basically that's our truth values there. We have true, false, vacuous truth, and vacuous truth. That is basically what the implies symbol does. It's a very, very unique thing, and it's very, very a bit of a pain. It's definitely one of those things that people get messed up on. There is also the biconditional thing, where why don't we go ahead and PQ. Alright. And then we do this. Boop boop. This is a bit short for what it's worth. But P Q, something like this. There is this. The reverse thing is basically the same thing as Q implies P, but you can also write it, but there is also a backwards arrow for your convenience's sake. And also the biconditional P and Q. Sometimes it's just faster to double click, even if you're fast enough, it doesn't really matter too much. Alright, there we go. This being the case, I'm sure, P, Q implying P, or you could also say, within this here, you could also word this as P when Q, such as, I'm not going to come up with a weird statement. P if Q, P is necessary for Q, and P follows from Q. And it's effectively the reverse statement, where, it's, P implies, Q implies P, P follows from Q. That's the one thing that actually makes sense for me. And this is false true. Well, this is then vacuous truth here. You have this. And true implies false, so that's false, and then false, false, vacuous truth. No, the VT does not stand for VTuber, by the way. It stands for vacuous truth. Although you could probably make up a random propositional statement that says something about VTubers that's vacuously true. If Pecora is saying, or actually, you know what? Since there's like the gamer awards that are popping up, so like, if I know there's like a joke that like Pecora is like insane or like a war criminal, so what's like a funny little thing that I can come up with? If all right. Well, I think I'll leave that up as an exercise to the viewer instead, to come up with a funny statement that implies, two statements that, when implied to the other, comes up with a vacuous truth that involves the game rewards. That's your YouTube homework. Come up with a neat little propositional statement that uses the imply to come up with a function that's vacuously true. You could also define a fake one as well, that doesn't involve VTubers, so long as P is false, and Q can be literally anything at that point, but so, that'll be left up to an exercise to the viewer, mostly because I can't be bothered to fucking do shit myself. Of course, we can also go ahead and, well, we don't really need to put that up on the chart up there. But biconditional, this is basically the truth table only really works because when it's in... Because here's the thing, it's basically when it comes to the biconditional statement, it's basically P implies Q, and P follows from Q. In other words, this is what it does. This entire statement here, all this stuff, gets and then its equivalency is this. And so these two are true. This one is false, so we don't have to worry about that. One of those is false, so that also just kind of happens. And both of these are technically vacuously true, so the bottom is true. And so now, what does this mean? For one, my nose is full of fucking burgers. Not burgers, boogers. You do not want to eat. You do not want to be eating these burgers. They're coming out of my nose. But you can also think of it as this. This, this is kind of implying, false is implying true, right? Or rather, true is implying false here, right? True is implying false, and we know that when if any of these variables, if a true variable, if a true proposition implies to a false proposition, then the entire statement is false. And so can this. So we're not just doing like and willy-nilly as well. You can also think of it as that. And because one of these things is like going to, true is implying false here, then this combination is false. However, when both of these is like like false, then effectively when you put an and operator onto it, it just becomes kind of true, because both statements kind of have to be don't worry about it too much. Even I didn't really get it either, and if you take a college class or talk to an actual professor in class who actually knows what they're talking about, who actually got a degree, unlike me, who decided to drop out of college because they couldn't handle all the homework that came with all this goddamn bull crap, then yeah. Anyways, let's go ahead and continue on to XOR. XOR, the symbol that I have written down in my notebook is actually a circle with a plus in it, and Q. I was pretty sure that the NAND symbol is an X, but, circle with an X. And we can go ahead and actually write that for this as well, where we're going to go ahead and have NAND here. We can go ahead and do that for what it's worth. You can always correct it later for the hell of it, but these symbols are the more consistent ones that I've seen. The OR symbol with a bar on top of it. That bar just stands for a not a variable. Basically it stands for negation the same way. So like, let's go ahead and do something like P here. Not P is a bit, it's also the same thing as this, where we just put a bar on it without an arrow. There we go. That's not P. Same thing. It's basically the same thing as parentheses, not P. But I'll go ahead and leave that there for what it's worth. And XOR, basically, for what it's worth, is the exclusive or also known, or the exclusive disjunction, is effectively when only one of the variables is true. If both of the variables are the same, if both of the propositions have the same truth value, like P and Q are true, then this entire statement is false. And let's go ahead and actually just put like a gray color here. You'll be using XOR a fair bit, but however, now we have P is true, but Q is false. So long as one of these is true, this is true. Same goes with the bottom, same thing. And both of these are false. They share truth value, and none of them are honestly true anyway, so this is also just false. Now, NAND is also a very neat function. I didn't really get introduced to it when I learned propositional logic to begin with. However, you can technically make every other logic gate from NAND. And basically, it's just the reverse of the AND symbol. So basically, it is false, true, 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 basically. That's basically it. That's the introduction for all of the crazy stuff, the functions and whatnot. So now the only thing we have to do now is exercise. Some exercises. And of course, I did not really think too hardly about how I was going to do that, but alright. So, I'm going to go ahead and copy the exercises that, well, actually, we can also talk a little bit more about propositional equivalence, because we know that, when we use propositional variables, these variables for stuff, we represent like different, we won't necessarily know what P or Q is. We're kind of just representing logic in like a very, very abstract way. And oftentimes we're not going to have like these concrete statements, and we can always just replace any or statement. So, if water falls from this pipe, then the sun will rise tomorrow. Like, it could be something as absurd as that, and for all we care about is like the general truth value of each, and whether or not like the whole function of it is true or not. And so basically a propositional equivalence is when A, which is representing a sort of propositional function, P and Q, and let's go ahead and make this a biconditional. And B, another statement here, is equal to Q kind of want to make the nice little proper not symbol that's like actually straight. And then this, where A and B are equivalent, basically equivalents, where of course we use a nice little triple bar to represent equivalence. And you can go ahead and actually try and prove that to be true. As an exercise, you can basically work it out if you want to, but I'd imagine that for what it's worth, it wouldn't be too hard to figure out that. But let's go ahead and move on to exercises. It's basically propositional equivalence is basically if our true compounds propositions are always true, if A can be interchanged with B more properly. Or why don't I go ahead and write that down? Propositional equivalence is effectively if A and B are true compound propositions, you know, that's I meant to say compound, but I didn't. It wasn't on the page with the other all stuff beforehand. So you just got to hear me say a whole propositional statement, which is basically the same thing but less fancy, which hopefully made it easier to understand, not harder. But compound is the more fancier, more proper way to say it. It's compound. A equals B if A implies B is always true. And we'll go ahead and do a little that's, and then there we go. Check it out. And why don't we also just underline this? Propositions and propositional equivalence. So basically, these two propositional statements are equivalent. They are the same, and there's quite a fair bit of propositional equivalence as well on my reference sheet as well, which makes logic doing a bit more easier. But for what it's worth, that's what it is. Now we can go ahead and move on to exercises actually, but I just realized I've reached the half-hour mark and I'm not sure if people want to exactly do that. So maybe I'll instead do that in a separate video, but that's basically all there is to the introduction of discrete math and propositional logic. Of course, some online classes start out with sets first, which isn't actually that bad. I didn't actually realize that you could start off. I'm just teaching it the way I've learned it, which has a bunch of propositional whatnot and stuff like that. But yeah, that's basically it. Thank you all so much for watching. I hope I didn't really bore you guys too much, but this is basically all there is to propositional logic. It is a fairly simple introduction. You know, there's only two truth values. We're not gonna consider indeterminate. And oh yeah, by the way, indeterminate's not even like the other truth values. There's like 4 value truth logic stuff and like 5 value and stuff like that I could not wrap my head around, and it made my head hurt. So just so you know, I'm starting you off. If you think this is hard, wait until you get into like the stuff out, you know, way deep into college and your studies. But for discrete math, for your very basics, and if you're learning to program, to do stuff, just to get introduction to logic and stuff, and also to solve weird, neat little puzzles by using these things called truth tables here. Why don't we go ahead and highlight that? This is a truth table here. Right here. Truth table. All these are truth tables because, you know, sometimes Sally and Bob and Andy are like all saying something and we know one of them is a liar, and given our propositional statements where some of their statements absolutely you know, have to be true or false, and we have to figure out who's the contradicting little twat, who's the liar, then you know, we basically have all that. But yeah, so we have these truth tables which help us prove equivalencies and also just kind of help us visualize all the different combinations and stuff. We have propositional variables, propositions, which are statements, which can, all these statements can be simplified to these propositional variables. We have all these functions, and we have truth tables and how they interact with each other, how these combinations interact with each other. The follows from statement, the P if Q statement, the P when Q statement, and the biconditional operator. And we also have equivalencies. And oh yeah, by the way, I'm also pretty sure that you guys are a bit confused as to what order you want to apply these variables in, because like say you have a very complicated logical operation which has like all of these, it basically follows in this order from top to bottom. The not operator, the and operator. Why don't I actually do this properly? The or operator. Oh, it doesn't, this actually, for what this is freaking worth, it doesn't have to be that steep, but I wanna do this a bit more properly, just to make it look nice. I'm an artist after all. I'll spend stupid amounts of time making things look nice rather than like actually getting to the point. And then we have the implies operator here. And then we have the biconditional operator. Basically, this is what I would like to call the precedence of logical operations. Which actually, why don't we move that down? Alright. The order of operations or precedence of logical operations. It goes from top to bottom. Ta-da! So there you go. That's it for propositional logic. There are a few exercises. There's more to it, including logic circuits and a bunch of other stuff, including identity, and we're gonna also prove some other stuff. We're going to also have to do some proofs and arguments, and you know, we are also gonna do fancy stuff like proof by contradiction, and we're also gonna prove uniqueness and use like some other fancy stuff as we go on with the crazy stuff that is propositional logic and logic in general. We start off with propositional logic, but there's more to this, including circuit logic and all that stuff. But for now, this is all you really need to know to really get by through the day. You can also do some exercises again, but for what it's worth, this is all you really need to worry about. So, once again, thank you all so much for watching. I hope they got enough for getting anything else. And yeah, have a nice day, everybody. And if you guys fall asleep, you guys are in deep enough sleep that I can like try and like put subtle suggestions in your head to like and subscribe and share this video with your friends who also like math and femboy VTubers, and try your best to like spread it with friends, because word of mouth is like the best way to advertise to people. And you know, to watch this video in its entirety, also turn off ad blockers specifically for my video and watch this video all over again so I get some extra ad revenue. You know, just to be nice and kind, you want to do it, and I'm planting that suggestion in your fucking head. I'm not trying too hard. If I wanted to, I'd try and like do like fucking more proper shit, but plus, it's not gonna fucking work on a YouTube video. You have to actually trust me to like actually relax enough for me to actually implant suggestions anyway, which is not gonna fucking happen, for one. But if you did like this video, though, please do like and subscribe and share it with your friends, because I really need that ad revenue. And yeah, of course we can also, if you guys want me to make another video that deals with some exercises proving some equivalencies, or making truth tables, going into logic circuits, eventually reaching arguments, what arguments are, and then going on to doing proofs of various things, then, yeah. I know I took this class like 4 or so years ago, but I still think that I still got the hang of it, but yeah. Anyways, I'm holding off the goodbye for a really long time now. I really shouldn't, but yeah. Have a good day, everybody. For reals this time. Bye.